Hi everyone, and welcome to the third of 4 videos going through some past exam questions on neutralisation and some bits of buffer solutions as well. So in this first question, you can see we've got some axes. They want us to draw some kind of neutralisation curves here. So we need to say what's going on. So an acid-base titration curve can be used to choose suitable indicators. We've got one with hydrochloric acid and sodium hydroxide, and they're at the same concentration. And we've got one that is the same, but they've got ethanoic acid instead of hydrochloric acid. Sketch pH acid-base titration curve to show how the pH changes when the alkali is added from a burette until the alkali is in excess. Okay, so in this first one then, we're starting off with the hydrochloric acid and the sodium hydroxide is being added out of the burette. So if we're starting with the hydrochloric acid, we're going to start at a very low pH. Okay, hydrochloric acid is a strong acid, so we're going to start with a very low pH. Because these are both 0.1 molar, so we've got 0.1 mole per decimeter cubed of concentration of each of them, then they should neutralize each other when we have equal volumes. So the equivalence point should be at 25 centimeters cubed. So we should have a vertical section of the graph at 25 centimeters cubed. Okay. So I'm going to put a vertical section in here. And then the general shape of the graph, remember, is that it's almost horizontal, and then almost vertical, and then almost horizontal again. Okay. And where are we going to end up? We're ending up with sodium hydroxide until the alkali is in excess. So we should be ending up at a pretty high pH because this is a strong base. There's no need for us here to actually calculate what pHs it should be at. It would be worth more marks than that. They would ask you to calculate it if they wanted you to do so. So as long as we're sort of roughly in the right ballpark, we're going to be okay. So we should be finishing up here at a pretty high pH. Okay, so we just want to level that off. And then we want to have it almost horizontal here, something like that. Okay. Right, and then this one should be the same. Okay, but the only difference is we've got ethanoic acid instead of hydrochloric acid. So ethanoic acid is a weak acid, so therefore we're not going to start as low down. Okay, the starting pH is going to be a little bit higher. So if I was here before, I'm going to come up here somewhere. Okay. They both still have the same concentration, so the equivalence point should still be at 25. Okay, so we should still have our vertical section at 25 centimeters cubed. And we're finishing up with the same sodium hydroxide that we had before, so we should be finishing at pretty much the same place. Okay. So we're going to level that off here, and we're going to put in something like that. Okay, so the only real difference between the two is we've just shifted it up a bit because we've got a weaker acid, so it's going to be a higher pH. And remember, this is the general shape for any of these pH titration curves. Okay, and then linked to that, explain how the choice of indicator is linked to the pH curve. So now that we've drawn this, how do we choose which indicator to use? So what we need is the indicator to be changing colour at the relevant point. So we want our indicator to change colour during this vertical section. Okay, it doesn't need to be spot on exactly at pH 7, because if we're slightly off, because it's vertical, it's going to give us the same volume anyway. So as long as it changes colour within the vertical section, we're okay. So we want to say that the pH range of the indicator, which we could call the end point, should match the vertical section of the graph. And remember, the vertical section of the graph includes the equivalence point. So we could use those terms as well. So you can use any combination here. So the pH range matches the equivalence point, that's fine. The end point matches the vertical section. The end point matches the equivalence point. Any of those combinations would be fine. Okay, then the other question that goes with this is linking it more to buffer solutions. So we've got this long, wordy question about how buffer solutions work. So it says a student is making a buffer solution by mixing propanoic acid with sodium hydroxide. It's got an equilibrium system. It minimises changes in pH when small amounts of acids and alkalis are added. Remember, that's your definition of a buffer solution. Okay, it doesn't keep the pH the same, but it does minimise the change in pH. So it keeps it nearly the same. So we need to do two things. We need to explain why a buffer solution has actually formed, and then explain how it controls the pH. Okay. So the key thing in this of why the buffer solution has formed is this word here, the excess. That's really important, that we've used an excess of propanoic acid. We need to talk about what's going to happen here. So when the propanoic acid is mixed with the sodium hydroxide, so we can say when propanoic acid reacts with, they're going to react with each other. Okay, this is our partial neutralisation. Okay, it's not just mixing the acid with its conjugate base. These two are actually going to react with each other. When propanoic acid reacts with sodium hydroxide, sodium propanoate is formed. Okay, so that is our conjugate base of the acid. But usually they want you to actually name it. They don't usually give you a mark for saying it forms the conjugate base. Okay, so it's good practice to actually write the name. So for a buffer solution, we need to have the conjugate base and the acid as well. And so the key thing is, because we've used an excess of the acid, after this reaction is finished, there's still going to be some acid left over. Okay. So we can say because an excess of acid was used, some propanoic acid will remain in the solution. And therefore we've got our buffer solution, because we've got our weak acid and we've got its conjugate base in the same solution. So that's this bit done. We then want to explain how this buffer solution controls the pH. Okay, and so it says here, look, in your answer we should explain how the equilibrium system allows it to control the pH. So we need to write out what the equilibrium is going to be. So we're going to have our propanoic acid, and the equilibrium is just going to be the acid dissociating. So then how is this buffer solution going to help us? Okay, so we can say when small amounts of acid are added, the H plus ions from the acid react with the propanoate ions. So this reaction is going to be happening from the buffer and the equilibrium shifts to the left. Okay, because we're going to be doing this reaction, we're going to add a bunch more acid in, so we're going to introduce more H plus ions. Those will react with the propanoate ions that are already here, and so we're going to be doing the reverse reaction. It's going to shift to the left, and that will get rid of the H plus ions that we added and keep us at roughly the same pH. It's going to minimise the pH change. Okay. The equilibrium shifts to the left. Let's just bullet point this so it's clear. When small amounts of alkali are added, the OH minus ions from the alkali react with, so we've got two choices here. You can explain this one of two ways, either is fine. You could either say that the OH minus ions will react with the H plus ions that are here, and then more of the propanoic acid would dissociate to replace them, or we could just say that the hydroxide ions that we've added will react with the propanoic acid, and either of those is fine. Okay, so I'm going to say OH minus ions react with the propanoic acid, and the equilibrium shifts to the right. Okay, because we're going to be using up the propanoic acid by reacting it with the hydroxide, so therefore we're going to shift this way. It's going to make water and it's going to make propanoate ions, so the equilibrium is shifting to the right. And remember, with this question, it's always the same. Okay, as long as you write your equilibrium out this way, which you would do because you're trying to show the acid dissociating, then alkali is always going to shift the equilibrium to the right, and acid is always going to shift the equilibrium to the left.